encryptions. Okay. Over here, we consider this three-party Alice and Bob. Alice and Bob want to communicate with each other. The man in the middle here is a special form of man in the middle. We call it eavesdropper or Eve, EVE. Okay. Over here, the Eve can see the raw data being transmitted. The Eve can listen, but Eve are unable to modify the data. Okay, recap that. I mentioned before that cryptography try to handle two cases. Want to handle a attacker who can see the data or the attacker who want to modify the data. In encryptions, we only consider one type. There is a if. The if can listen, try to extract useful information, but if will not modify it. So how can this be possible if can hear, can intercept and see the raw transmitted data and yet unable to get useful information? How is this possible? Okay. In encryptions, we use this idea of having a secret key. Okay. Over here, likewise, we have three parties, Alice, Eve, and Bob. Okay. Alice and Bob, both of them know a secret key. You can view it as like a password. Okay, both of them know the secret key. There are two processes or algorithms. One algorithm is called encryptions. One algorithm is called the decryptions. Okay. So Alice, okay, have a message to send to Bob. That message sent to Bob, we call it the plain text. For example, in this case, meet in library. Meet in library is the plain text. Alice would use the encryption algorithms that taking as input the plain text, meet in the library, and the secret key, some can be some form of password, okay, and run the encryption algorithm process. This will give a cybertext. So in this case, the meet in library become n%x3da or something. Okay, I just these are basically some random character I put it in. Okay, it doesn't make sense. Okay, yeah. If the man in the middle here can see this cybertext, and the on the Bob side, Bob also received this cybertext. Okay, if this cybertext will be transmitted from Alice to Bob going through Eve. Bob, after receive the cybertext, will run the decryption algorithm using the cybertext and the secret key. Okay, and after decryptions, Bob will get back the original plain text, which is meet in library. Okay. This key is important. The key K is to be a secret. It's a secret, okay, to be known by Alice and Bob only. Okay, on the whole world, only Alice and Bob know the key. In particular, Eve doesn't know the key. If Eve doesn't know the key, from the cybertext, the n%x3, so on, Eve will not able to make sense of what it is, unable to extract the information of meet in library. Okay. Bob, on the other hand, because Bob knows the secret key, can run the decryption algorithm to get the plain text. Okay. The key K is fixed. Okay, when Bob and Alice agree on a key and fix, and it can be used many times. For example, this key can be used to encrypt plain text, a message Alice want to send to Bob. It can use to encrypt a movie, or a music file, or an image, okay, and use it repeatedly many times. Okay. So here is a first question, very simple. I just want to stress the importance of these 5 things. There's something called plain text, key, ciphertext. Right? We take the plain text, use the encryption algorithms that to taking the plain text and the key to get the ciphertext. And we take the key and ciphertext, we run the decryption algorithm, we get back the plain text. And who know the keys? Very important. Only 2 persons know. The sender and the receiver, Alice and Bob. Okay. Let us look at some examples. Substitution cipher. Okay. Cipher is also a name for encryptions. Okay, I highlight this. There's in red. This cipher we may see in the storybooks. Okay, but then it's not secure. It's just for illustration, okay, to illustrate certain concept. Substitution cipher is very simple. Okay, there is of course, there's a plain text. For example, in here is hello world is a plain text. The plain text, we need a key to encrypt it. The key is a table, a substitution table, as you show in the slide, A, B, C, D, E, F, G, up to Z, plus a space. And the table say that A will be mapped into G, B will be mapped into V, C will be mapped into W. Okay. So hello world, H will go to H, E will go to N, L will go to U, and so on. So during encryptions, Alice will take hello world and using this table, build the ciphertext. Bob, after receiving the ciphertext, can recover back to the original plaintext using this table again. You look at H, H go back to H, and look through a table, oh, N will go back to E, okay, and so on. Okay. Let's use the CyberChef as an example. Okay, you go to the website. You can choose the cipher. Over here is a substitution cipher, and key in the plain text, and key in the identity, and the corresponding key. Okay, the ciphertext here is over here. The plain text A, B, C, D, E. This is to Z, and the corresponding ciphertext. This actually give the substitution table. Okay, after we establish a table, then you key any input, the plain text, then you get the ciphertext. Okay, so take special note over here. This plain text and ciphertext actually refer to the substitution table. Okay, now suppose we are an attacker. What should we do? We are an attacker. Okay, we are an attacker. We are like if, and we as an attacker, we receive the ciphertext. Okay. So what would the attacker do? Okay, so we have to understand the attacker before we can defend. Okay, so when we look at what attacker do, we have to describe the attacker. Basically, we have to describe 2 things. 2 important things to describe. What is the intention of the attacker? What is the attacker goal? If obtain the ciphertext, is her goal to find the secret key? Or maybe she doesn't care about secret key. She just want to find out what is the plain text. Okay, this is the goal. And what actually does attacker have? Okay. And does the attacker know the corresponding plain text of some ciphertext? Recap that just now I highlight that the secret key is to be used many times. Use it to encrypt a message, you encrypt second message, or use it to encrypt the video or images. Right? It could be possible that attacker somehow capture the ciphertext and know the corresponding plain text. Okay, that is encrypted using this key. Okay, he know a few. Now, given something extra, the attacker want to figure out what happened next to find the key or find the plain text. Okay, or in this case, in this type of cases, we call it no plain text attacks. Attackers somehow know the corresponding plain text of some ciphertext, encrypted using the same key. Okay, important, huh? Is same keys. Or the attacker doesn't have this historical known plain text, okay, and the corresponding ciphertext. Attacker receive the ciphertext, but he know that the plain text is English sentence, right? Okay, so in this case we call it ciphertext only attacks. Okay. Over here, I list the basic goal and basic capability. Okay. In general, they are much more compounds or more complicated goal or capability. For example, in attacker goal, attacker, suppose we think that we are Eve, we intercept a message, okay, intercept a ciphertext. Our goal maybe is just to figure out whether the plain text, whether this is an encryption of a image or a Word document, right? So as an attacker, I capture something, okay, and I just want to know whether it's words or images, right? Attacker capability. Okay. Attacker could be have more. For example, we know that in a smart card, okay, attacker probably have capture a smart card. A smart card contain a secret key. Okay. Attacker can continuously query this smart card, sending it plain text, then the smart card will encrypt for him. And the attacker goal is to find out the secret key. Okay. So this capability is of another level. Okay. Anyway, in this session, let's keep it to these two simple goal and capability. You look at it, substitution cipher is immediately not secure. Why is this so? Substitution cipher, under known plaintext attacks, we can immediately get the key. For example, suppose attacker know that hello world is a plaintext of HNUUQPOQIUB. Okay, attacker know this. Can he construct part of the table, the key? Yes, he know H is mapped to H. E is to N, L is to U, O is to Q. Right? Easily constructed the key. So in this case, substitution cipher is not secure under known plaintext attacks. Okay. So cannot be used. Okay, it's not secure. Immediately, it's not secure. Okay. Okay, even we know that it's not secure, let's investigate it slightly more. Okay. What about ciphertext only attacks? Suppose attacker is given a ciphertext, the if, intercept and capture this one. This is a ciphertext of something, right? And somehow attacker know that the plain text is an English sentence. Okay, it's an English sentence, okay? And can the attacker get the plain text? Surprisingly, the answer is yes. Okay. Through experience, we know that suppose the ciphertext, okay, the plain text about size of 60 character around there or 30, 40 characters, and know that it's English sentence, with very high chances, we can get the plain text and the key. Yeah. Why is this so? This using something called frequency analysis. Okay. This wiki page have a good explanation on that, and you can go and click and find out. But let me tell you the key idea. Let's look at the alphabet A and Z. Okay. A will be mapped by substitution to some character. Okay. Let's say to B. A is to B. Z is to C. Okay. A is to B, Z is to C. Let's suppose in this case. Now, we know that in the plain text, in a typical English sentence, A occur much more times than Z, right? You look at a typical English sentence, oh, there's many A, and very few Z. Okay. Now you look at the ciphertext. The ciphertext inherit these properties. Okay. A is being mapped to B, so B will occur much more time than C. Okay, Z is mapped to C, right? A is mapped to B, Z is mapped to C. So in the ciphertext, B will occur more frequently than C. Then as an attacker, I made a guess that B in the ciphertext, B correspond to A. Okay. And by doing this guesswork, okay, it turned out that it's quite easy, even just using pen and pencil. We don't need computer, just take a piece of pen and pencil and we can get it. So now the question come to question 2. What is the plain text of this? Okay, I let you try. Okay, there will be some tools to help you, will be easy. Okay, one way to cheat to do this is that you go to Google, download some simple some apps can actually directly decipher for us. But try to do you try to use pen and pencil, okay, rather than relying on that. There are those apps. Okay. There are also some tools that can probably help you. You take this one here, help you to count the number of characters. Okay. Okay, substitution is not secure. Okay, so what is secure? When we call modern cipher, we refer to encryption scheme that is to be used in this computer era. Okay. We will not go into detail. Just take note that modern cipher are designed, when they design it, they take in consideration of the threat where the attacker have access to many additional informations. Okay, for example, no plaintext attacks, and there's something what they call encryption oracle. Okay, and they want to achieve very modest goal. Okay, that means that when we design the encryptions, modern cipher, we taking account that we are facing an attacker who has many information, very capable. Their capability is very high. We are facing an attacker like that. And the attacker want to achieve very little. Modest goal. The attacker want to achieve very little. He just want to distinguish whether the ciphertext is an image or Word document, for example. Okay. So why we do that? Why we do that? This is because if we have a scheme that can protect against attacker who is very strong, have many informations, then I can define against attacker who have fewer information, right? Okay, and if my method can deny attacker to achieve a very little goal, then my method can also deny attacker to achieve a very difficult goal. Right. So that's why we take into we use we want to design against attacker, okay, with a lot of information and modern scope. And modern cipher, in fact, is designed in this way. And it took the community a lot of smart mathematicians and computer scientists to build that. A widely used method, okay, is called AES, Advanced Encryption Standard. Okay, this standard is believed to be secure. Okay, it's designed to be a block cipher. Okay, it's a block cipher. What does a block cipher means? Well, AES as a standard, as an algorithm, okay, the input size is fixed, must be 128 bits plain text. That means 16 bytes. 16 bytes. So the input is fixed. The output, the ciphertext is also fixed size, 16 bytes. The key can be 128 bits, 192 bits, or 256 bits. These are specified in the standard. Although I mentioned substitution cipher is not secure, AES, you look at the design, substitution is one of the components, important components, and the other component is called permutations. Okay, now you may wonder, so many smart mathematicians and computer scientists, after so many years, they design an encryption scheme which is a block cipher. That means that the input is only 16 bytes message. However, a lot of time we want to encrypt very large thing, right? We want to watch a 7 GB movie. So what can we do? So the matter is this. Okay. The AES is designed as a block cipher only taking 16 bytes. We next need another method to extend it to very long messages, arbitrarily long. The method to extend it to very long messages is called mode of operations. Mode of operations. Okay. And we will discuss two mode of operation. There are many. Let's describe two. Okay. First one, ECB. ECB okay, is a very straightforward way of doing things. Okay. So one may wonder what's so difficult. Okay, this thing work for 16 bytes is in one block. If I given a 7 GB movie, very simple. I just break the 7 GB movie into smaller pieces of blocks, like we show here. In here, the plain text consists of 3 blocks plus many others. Okay, so take the plain text, divide them to blocks. Every block 16 bytes. Okay, and then we encrypt them. We encrypt them using the secret key, right? So I take the first byte, the first blocks, take the secret key using any AES encryption to get the ciphertext, one for that block. I repeatedly apply it to the second blocks, third blocks, and so on. Okay. This method is called ECB. Okay, I believe this will be the first thing that comes into our mind. Okay. This method, as I highlight that, is not secure. Okay, he leak informations. The attacks have an interesting name. It's called ECB Penguin. Okay, I will describe it later. Okay, why it's called a penguin attacks. And the other mode is a secure way of doing it. It's called counter mode. Counter mode is a type of a stream cipher. Okay. So to encrypt a plain text, likewise, we divide into blocks. Let me show you the process. Okay. First step, okay. We are first, okay, let me repeat one more times. For counter modes, okay, remember what is the input? The input is a secret key, the red color secret key, and a large plain text. Okay. First step is to randomly choose a 16-byte value called the IV. Okay, it's initialization vector. Okay, choose an IB, randomly chosen. It's supposed to be randomly chosen. Okay, choose some 16 bytes. That means 128 bits IVs. Then the encryption is actually done on the IV. Okay, we take the IV, encrypt it using AES encrypt it. Can you see in the slide to get one blocks, these blue blocks. Okay, I take the IV, encrypt it using a secret key, get the blue blocks. Next, change the IV little bit, increase by 1. What do we mean by that? These are binary sequence. I believe most of us know what is a binary number, right? We treat this as a binary numbers and increase it by 1 plus 1. So in this case, it become this 1011, 1001. Increase it by 1, add 1 to it. So this value next will be encrypted using the same key to get this. Next, we repeatedly do this process, increase it by 1, encrypt it, increase it by 1, encrypt it, and so on. So from an IV and a single key, we get a sequence of blocks. Let us call this pseudo-random sequence. Okay. If we visually look at all this sequence, it will look like random, but they are not truly random. They are pseudo. Pseudo means fake. Okay, they are not truly random. Okay, you look random, but it's not. Okay, so let's call this pseudo random sequence. They are not truly random because they are generated to 2 by 2 value, very short piece of information, the IV and the short key. Now, given the plain text, the 7 GB movie, we divide the 7 GB movie into blocks of 16 bytes. One 16 bytes, one blocks, another blocks, another blocks. And next, we take the pseudo-random sequence and XOR with the plain text to get the ciphertext. I will describe what is XOR later. Okay, we take this one, which is 128 bits, and this one 128 bits, XOR them to get another 16-bit, 128 bits. We likewise repeatedly do it for the rest. This will give a sequence of what? Of ciphertext. Okay, so we get a lot of these yellow blocks. So the final ciphertext are final ciphertext are all these together, important, together with the IV. This IV will be put in here, and this one here, and all of them collectively become the ciphertext to be sent across the channel. Eve will see it, Bob will receive it, and Bob will try to recover the plain text. Fine. Okay, so let me repeat the important part. The encryption requires the key and the plain text. In the process, during encryption process, IV is generated. Okay, and through all this, you get all the yellow part. The ciphertext consists of the IV, the one that generated by the encryption process, and the XOR of the plaintext and the pseudo-random sequence. So now let me describe what is XOR. XOR is an operator, okay, binary operator. Okay. The symbol is this plus with a circle. Okay. If I 0 and 0, 0 XOR 0 will get 0. 0 XOR 1 will get 1. 1 XOR 0 will get 1. 1 XOR 1 will get 0. It's called exclusive OR. Yeah. You can view it as this is actually addition modulo 2. 0 plus 0 equals 0. 0 plus 1 equals 1. 1 plus 0 equals to 1. 1 plus 1 equals to 2. But 2 modulo 2 is 0. So 0. Okay. So suppose this is a plain text 0, 0, 1, 0, 1, 1, 0, and these are the pseudo-random sequence R generated from the IV, 1, 1, 0, 0, 1, 1, 1. Then the ciphertext will be 0 XOR 1, 1, 1, 1, 0, 0, 0, 1. So X XOR R, we get C. XOR have a very interesting property. You take C, XOR R, and we get back X. 1, 1, 1 XOR 1, 0, 1 XOR 1, 0, 1, 0 get you 1, 0, 0 give you 0, and so on. Okay. So just to refresh what we have learned, in the counter mode, that means the string cipher, thus if C the IV, if is the attacker, the man in the middle, right? If C the ciphertext, would if able to see the IV, is IV a secret to if? The answer is if can see the IV. Right, look at this. This is IV, and put it here, this part of ciphertext. If see the ciphertext, so if see the IV. Okay. Our slide only show how encryption is done. How is decryption? How about decryptions? Okay, so this is encryption process, right? From the key and plain text, you get a ciphertext. From the key and plain text, you get a ciphertext. But what about the other way around? From the ciphertext and key, can I get a plain text? Okay. Yes, and I leave this as an exercise for you.